Okay, we're going to look at trigonometric graphs, which are sine, cosine, and tangent graphs. They're not just functions that you can use to find out triangles. In fact, they're not actually even generated from triangles. Well, they are sort of. If we look at a unit circle, so a unit circle is a circle of length of radius 1. Okay, and we look at this circle and we look at the radius and we look at an x-axis. So the x-axis was going through this circle. Okay, now if I want to find the height and the distance, the vertical and the horizontal distance away from the center of this point, we use trigonometry. If that angle is theta, then I can work out these two lengths. Now this length here is sine theta is equal to 1 over this length divided by 1. Now this length divided by 1 is obviously this length. Now this length divided by 1 is equal to sine theta, and so this length is just sine theta. And similarly, this length here divided by 1 is equal to cosine theta. So this length here divided by 1 is cosine theta, so this length is cosine theta. Now as if I start from here, my angle is 0, and I go round my circle, sine obviously theta is 0 here, and then it goes up to at 90 degrees 1, then it goes to 0 again, and then as it goes around to 270 it's minus 1 because this is positive 1, that's negative 1, and then it goes back up to 0, and then at 360 it repeats itself. So it's got a period every 360 degrees it repeats itself. Now cosine theta starts here at 1 because it's this distance here, goes up at 90 degrees to 0, 180 degrees minus 1, 270 degrees is 0 again, and then back up to 1. So again it repeats itself every 360 degrees as we go around. So if I was to draw the sine theta graph, that's what it would look like. So this is degrees, 360, so it goes up to 1 at 90, 180 back to 0, 270 minus 1, and then up to 0, and then we repeat ourselves. And if I do negative, which means in fact instead of going that way I go this way, then it's just repeating itself. So this is called a sinusoidal wave, and it's used a massively amount in engineering for vibration and to do any sort of oscillation. Now if we look at the graph and I want to say, okay, find a value, I can say that sine 30, if I look here at 30 degrees, go up from 30, go across, is a half. Okay, and in fact if you put that into a calculator, sine 30, it comes up as a half. Now clearly that's not the only place where the graph is a half. In fact it's a half an infinite amount of times, because this carries on in this fashion no matter what we say, because every 360 degrees it repeats itself. So we need to find out what other angles, so what angle is this, what angle is this, etc, etc. Now all of these, if I put in sine of something, whatever that angle is equal to 0.5, a half. Now you don't need the calculator to work these out. You can use symmetry, because you know this point here is 90 and this is symmetrical about that point because of the way it goes around a circle, and this is also symmetrical to this but in a negative fashion. So I can work this out here by figuring out, well actually how far away from here is this value, and I know it's the same distance away from here. Okay, so sine 30 is also equal to, I know the point is 180, this distance here is also 30 degrees, because this distance here is 30 degrees, and so this value here must be 150, because the distance here is 30 degrees, and so this distance here is 30 degrees, and I know it's symmetrical and so I know that this is 180 and this is 0, and so I know that this value here is 150. And I can do the same here. I know this value here is 360, so 360 plus 30. I know this value here is minus 180, so minus 180, take away another 30. I know this value here is minus 360, so minus 360 added on to 30, because I'm moving closer to 0, gives me the values there. And so I can say the same each time. So this value here is obviously 390, this value here is minus 210, this value here is minus 330. And I can, in fact, once I've found these two initial values, because in your calculator, when you put in sine, inverse sine of something, it only gives you values between 90 and minus 90. You can just add or take away 360 from these two values, and it will give you all the other values, because it repeats every 360 degrees. Okay, the period is 360. Okay, right. So let's have a look at the cosine graph. So the cosine graph started off at 1, and it goes like this. As you can see, it's exactly the same as the sine graph, just translated 90 degrees along. Now, if we do the same thing, so say I want cosine of 60, cosine of 60 is also a half. I can do exactly the same thing, look along the line, find out all the other values, and use symmetry again. So here I know that it's symmetrical about this point, so this distance here is 60 degrees, so this point here is minus 60 degrees. This point here is going to be from this point here to here is 30 degrees, because this is 90, and so where we cross the x-axis, this point here along is also 30 degrees. Or I could go from this point here, which is 360 degrees, and that's 60 degrees back, which gives me 300. So looking at the same thing, I can do the same thing. It's symmetry, 300 degrees, minus 60. That should be minus 300 degrees. In fact, in general, cosine is slightly easier to work out than sine, because in general, the cosine of theta is equal to the cosine of minus theta, because the graph is symmetrical about the y-axis. Okay. Please note also that cosine and sine, the values can only take values between 1 and minus 1. They don't get any bigger than that, and that's because it's the radius of the circle, the unit circle. Again, this has a period of 360 degrees, so it repeats itself every 360 degrees. Okay, so we look at tangent. So the tangent, if I extend my line out, the tangent of the circle is that. And what we're looking for is this distance here. Now, this distance here, as we start here, is 0. And as we go up and up and up and up, when we get to 45 degrees, because this is a right angle, because it's the tangent of a circle, this is 45 degrees, means this angle is 45 degrees or here. And it means that that's an isosceles triangle, which means this side is 1, this side is 1, and this length here is root 2. So because this length is also 1, this length here you can work out as root 2 minus 1, which is about 0.4. But this is how you work out the tangent. Now, as you can see, as we get round to 90 degrees, then this then becomes parallel to this. So that means that this doesn't touch this. Okay, so it becomes not defined, because there is no point where it crosses. But as you can imagine, at 89 degrees, this is going to go on for ages and be a massive value. So tangent actually takes values between 0 and plus or minus infinity, because as I get closer and closer to 90, this line becomes longer and longer and longer and longer. And when we go back on this side, the tangent then is on this side, and so it becomes onto this end, and so we get a negative value of the tangent, because it's on it's hitting the x-axis in a negative place. So the graph looks like that. Now here we have asymptotes at 90 degrees, 180 degrees, sorry, 90 degrees, 270, etc., minus 90, minus 270. And so these are the values that the graph gets very close to but doesn't actually touch. Now I can do the same for tan as I've done for the others. As you can see, this repeats itself. This repeats itself every 180 degrees. And so this has a period of 180 degrees. So if we look here, tan of 45, we already said from the graph is 1. And so we know that. Now I can do the same, look along. Now, luckily for me, tan is much easier to do because we don't have like a reciprocating thing like we do in cosine and sine. It's just the same graph translated 180 degrees. It actually repeats itself every 180 degrees. And so tan of 45 is tan 225 minus 135. And so all I have to do is just add on or take away value multiples of 180 degrees, and that gives me same value, or each of these angles is the same value. Now, so okay, period 180. How do we look for and use that? So work out the other values for the angles between minus 360 degrees and 360 degrees inclusive of sine 130, or where tan theta equals 8. So sine 130, you don't actually have to work out what it is, but it's roughly about, I don't know, 0.8, as you can see from the graph. Now, we know this angle here is 130 degrees. We know the distance here to here is 50 degrees, and so I know that it's also symmetrical about that point there, and that's 50 degrees in from this point here, which is 0. Okay, so I know that, and it's there, there, and there, and I know so theta equals 50 for this first one. This second one, because it repeats every 360 degrees, I know that this and this are the same. Okay, but 50 plus 360 clearly is outside of this 360, so we don't want that one. Okay, so then I can do take away 360, so 50 take away 360 will give me this value here, which is minus 310, and then I can do this value here, which is 130, take away 360, and that gives me minus 230. And so those are the values between minus 360 and 360 where that are equal to sine 130. Now notice I didn't actually have to work out what sine 130 is. If you can work out on your calculator, but if you put it, that in, it will just give you this the value here, and that doesn't really help that much. So let's have a look at the second question where tan theta equals 8. Okay, this time tan theta is 8. If you put inverse tan theta, it gives you 56.3 degrees. Now I know it repeats itself every 180 degrees, so 56.3 degrees plus 180 gives me 236. 56.3 degrees plus 360 gives me, actually this is not 8, it's 1.5. 56 plus 360, which is 2 lots of 180. Again, we don't need that because that's clearly outside of 360. So we do 56 minus 180, and then 356 minus 360. Okay, and that gives us our values there. It's fairly straightforward. Do the exercises in the book, and I'll send some questions next week.